Well, welcome to the first ever SATlive live stream. My name is Thomas Neumann. I'm the developer of SATlive, and today I try to show you a thing which is very important when it comes to dual-FFT, which is time. And I'll show you a little bit here what is dual-FFT and why time is important when we do this kind of measurements. Yeah, I will show you some examples with using SATlive. And as I mentioned before, it's the first time I'm doing this in this way. I'm looking for your feedbacks. You can use the comments at comment, and I hope you can hear me and hope you're feeling fine. Yeah, let's start. Well, the basic thing is very simple. We just have a simple situation. We've got a simple cable here that we want to measure. And we have a computer, which is not shown here, and we have an audio interface. With, is in this case, with Dante, but it's just a way to get audio in and the audio out of your computer. So, what we would do instinctively, if we approach this thing, we would just plug in the cable in one input and connect it to an output in order to send some signals through this cable, which would lead us to something like this. We have one input, we have one output, and we will send a signal. Well, this signal could be anything, but it will don't give us much information. So we use normally for this approach a certain signal which is called pink noise. And why do we use pink noise? We use pink noise because we assume that pink noise has a flat overall energy spectra, which means that we think when we see a flat response, all frequencies present with the same energy, we will have the cable with a flat transfer function. So, and if you do this in measurement software, here we have something I'm sure you've seen before. It's so-called RTA measurement. We just now sending out here a pink signal into our cable and monitoring what's coming out of our cable into one input. And you see here we are using pink noise, so we assume we will get a real flat response, but well, it looks flat, but you see it's jumping around. So to smoothen it out, we can use a longer time for averaging, and you will see it will start averaging out to something that's let's say nearly flat, but still it's a little bit jumping around. And this is simply because the assumption that the signal has the same energy at each frequency span is true, but it's only true if we look on our signal for a very long time. So if we do a very, very long measurement, we will get really a flat line. But you know, it's no special thing. It's not a room or something critical. It's just a simple cable we are currently looking at. And so you see the RTR approach, the approach sending a certain signal into this cable and looking at the output will give us not the information that we really want in a feasible time. So using an RTA makes sense if you want to monitor some energy in a signal, like on a feedback or something like that. We want to see where is the most amount of energy, or where is the ringing frequency of our snare. But for a measurement of a transfer function, when we want to know how good is our cable or room or whatever we're going to look at, transferring certain frequencies, this is not the way to go. So this is why some people thought, oh, what can we do now here? How can we overcome this problem? And they found a solution which is very simple but genius at the same time, which is the dual-FFT. In the dual-FFT, we add a second measurement. So we not only look on what's coming out of our cable, but we are also looking on what do we send into our cable. So we have here, as you see with this red line, a connection between the output of our device directly to one input. And the input where we put this signal in, the copy of the output, is called reference input. This will give us two inputs, hence the name dual-FFT, and now we can compare both inputs. So we now know what is in this moment, which energy is sent out, and so it's easy to compare. We do not need to rely on specific performance of our signal, because we know both. We know what we send out and we know what we get back. So I just switch back to SATlive. I hope here. So, and now still here is the same as before. Now if we use two inputs, so we have two RTA sections here. If we use it side by side, we see it's still jumping, especially in the low frequency area, but both bars are on similar highs each time, because we're looking on the output, which is the green one, the reference signal, and on the blue one is the input. So both are same in level, same, not exactly the same all over the frequency, but here they are same. So if we just go away from looking on these two signals, and now we go to look on the relationship of these two signals at each frequency, this brings us to the transfer function, and the transfer function is just the difference between both signals. And you see we are looking on a cable which is perfectly flat, does not add anything, does not remove anything, so we're gonna get a flat response. Now we got, even here we see two lines, and this is a thing most people are a little bit confused when starting with dual-FFT, because we have two signals, but we have just one result. But this result contains two parts. One part, which is the upper one, is a so-called amplitude response. This is the thing we normally know and see in every data sheet, which just tells us how fine different frequencies are transferred here. And as you see, it's just flat, which in SATlive this is the upper trace. The lower trace is so-called phase trace, and phase is a thing that is in some way related to time. I don't want to dig too deep in this in the phase thing today, because I think it's worth an extra stream. But just keep in mind, on the top you see the amplitude response, and on the bottom you see the phase response. So still there's no timing things here, there's no delays involved. And the next step we use, now we are able to measure our cable, which is nice, but it's not the thing we normally do in PA system live sound reinforcement. So our problem looks more like this in the real life, which just means that we have one input, one location, we have a speaker somewhere, more speakers, and a measurement microphone or more measurement microphones. And we just want now to see how good is the transfer between the output of our desk to the location where our measurement microphone sits. So yeah, we can try in earlier days, they tried to do it in a similar way with using playing back pink noise and looking on CRTA, which yields a picture which is similar as one as we've seen before. Here we have just the output feeding the speaker. I just drop off power amps and things here just to show you the principle. And we have a measurement microphone also connected. And if we do so, which could be done here easily in SATlive here. We will get something like that layout here. This one. So now we are looking on the output signal here, or just some kind of speaker. You see we are sending out pink noise and hoping, expecting a flat response, but we have the same problem as we've seen with the cable. And the solution is basically the same as we did on our cable thing, just add a second input which will receive the information of the signal we send out. So if you do this here, looking in the RTRA, we see on the bottom there is our reference signal, the spectrum of the signal we send out, and at the top we have the signal that is received by our microphone. So the thing which represents the speak in a way. So, but you see it's jumping. There's no timing information anymore. So yeah, just we do the same as we did with our cable. We just use these both signals and compare their content and go to the transfer frequency. And if we do so, you see we got response and that looks fine or readable up to approximately 1K, and above we got strange things, and our phase trace on the bottom also looks very strange. So now the question is, why is this the case? And it's very simple also, and this is now where time and delay comes into place. um, when we look on our setting for the room, you see we have two ways that our signal will travel. One way is directly from the output to our reference input, and the other way is much longer, takes much more time, because it goes out of our interface, it goes to the speaker. It might pass a digital controller which adds latency. It goes to the speaker, and most of all it travels through the air to our microphone, which also takes time. So we are not anymore comparing the same signals, because as you think, when we use snare hit as measurement signal, we will see the energy of the hit first on the reference input and after some time on our microphone input. And so we are comparing things that are not really related to each other. So to solve this, so to overcome this problem, we need to add a delay in our reference chain. A delay in the red line here, in order to time align both signals to be able to compare this. So when we go back here and I start my measurement again, you see we still have no delay, and if we set the delay, tap it by pressing Ctrl D, for example, or using some function other, you see we get a really nice measurement over here. And yeah, but important, I want to show you here, you see here in the bottom, you see a delay value. So that means this is a delay which we've added to our reference signal in order to compare similar signals to each other. So it's when we do dual-FFT, it's really is important to set this delay right to get a nice and meaningful result. But this also will introduce a problem, because we can, as you can imagine, if we're doing a cable measurement, which I'm going to do again right now here, you see, first of all, you see it's also getting strange here, the results, because the delay is wrong. So if I reset the delay to 0, we are here. So now we can measure this signal, and we can store it to one of the stores. So let's say full flat here. And now we accidentally change our delay setting here just for a few samples. In fact, now we just changed it with 2 samples. So we still have the same cables that we are measuring. We do not change anything of our things we measured. But you see, we have a really visible change in our phase trace. So now we have 2 different looking results of the same thing that we measured. And this is one of the points you have to be really aware of when you're doing dual-FFT, especially when it comes to comparing things in time, because we have different time. When we have different times used for measurement, you can't compare phase traces. You still can compare amplitude response, which is not critical for the things, but you can no longer compare phase things. And If you want to do some post-process like you can do in SATlive, we have two measurements, both of the same cable, absolute the same thing we've measured, and now we want to add both measurements to see what's happening if we add both things. So it's cable, it's trivial, but it's easy to show it. So if we add it, we can do this here with using this, okay. And we add it without doing anything. You see, we got, which here is pinkish trace, is the result, the overall result of the addition, which is on lower frequencies. It's really nice to 6 dB. So it's everything as we expected, but on here are around 12K, we have a perfect cancellation. In our post process, we still have the same cable outside. We did not change anything here. So it's really important to keep this in mind. So if we want to do something like time alignment or something like that, we need to have the same reference time for both measurements. We want to compare in the phase. We want to use it for some calculations. And with SATlive, there are some tools that can help you. So, for example, if we do this measurement and we want to compare our measurement to the other measurement we did before, here's a yellow line, and we don't not remember which delay we've used when we did this measurement, we can just go to our delay menu. No, sorry for this. Here we are. Let's use the symbols. Now we can import this delay. Yeah, we can use it here, and we'll get the same delay. Or we can, if you go back, we add this delay again, and we want to hide trace in the moment when we activate our post-processing feature, like the addition, we get a message which says here, states the measurement delay differs from the delay used for current measurement. So SATlive asks you, shall I compensate for this delay for the calculation of the addition? So you say, okay, yes, do it. And you see, now we got perfect addition, because both measurements were taken with the same cable, with the same flat response, without anything that affects time. So, but if you look here, we would expect something else. So it's a difficult thing here with time. Just we need to keep in mind that we're working always in dual-FFT based on the reference time. And as soon as we change the reference time, we are not able to compare to results related to phase. So this is very important, and this is the reason, because everybody says if you do time alignment and you've set your reference delay, do not change it. The reference delay also affects impulse response measurement, which is also related to this delay here. So if we go just a little bit further, you might see just another look. You see, we are not on 0, even if we are just currently using our cable for the impulse response, but we are on minus 166, which is the same as the delay, the opposite of the delay. So we just are here on 0, but in the display we are shifted. So again, take care of this time setting when you're doing FFT, dual-FFT, because on one side it's important to get nice looking and readable results, and on the other hand it's dangerous because it can spoil your signal, or it can make it incomparable to something you've stored. So this is why normally SATlive does not adjust this delay for measurement automatically. SATlive is able to do it, can do it. So if we go in our menu, we have an option auto adjust delay over here, which would do this. So if I add some delay here, you see just readjusts it and adapts for the change delay, but shows here a red square just indicating you the coaches. Your SATlive will adapt the delay automatically. So, hey, for myself, does not like this. I like to adjust the delay for myself. But if you're going just for EQ curves and you are taking pictures on different locations in a room, this might be helpful. But you must consider that you just take pictures, amplitude responses. It does not make sense to look on phase responses that are given in such a case. Yes, so I think this is the thing I want to tell you, that this value, the delay between the reference and the measurement input, is very critical for your measurements. And if you have any questions related to that subject, please type it in the chat. Otherwise, you will find SATlive on the webpage www.satlive.audio, and you can download the demo version and try it for yourself. Yeah, if you like it, you know, the things thumbs up, and I think I'm gonna do some more of this streams for different subjects. I think phase is very interesting thing. I'm not sure if I can handle it in one stream and other things, but I think it's nice to have a look on this timing thing. Yeah. So, thank you for watching, and stay safe, and yeah, you may leave your comment or suggestions or questions. I will answer the questions either in the chat or the comment section, or yeah, if it's an important thing or a thing which is difficult to explain in written words, I might be covered in the next stream. Okay, see you, bye.